Hey everybody, I hope you're having a good summer so far and that the course is going well. I know that starting probably around chapter 4, chapter 5, the material started to pick up and things are getting a little more complex, and they will continue to get that way. So make sure that you're keeping up with the readings and letting me know if you have any questions at all about the material. Today we're going to start getting into chapter 6, and in chapter 6 we'll talk about three major topics. There's decision errors, effect sizes, and what we call statistical power, or sometimes just power. And to keep spirits high, I've put a picture on this cover slide of my niece who I'm visiting right now. I'm actually in Boston. You might notice a different background. I'm staying with family in Boston and visiting my young niece. So there's a cute picture of her. We'll get started on the right foot. Okay, so this chapter, anyway, is a chapter in which we're getting beyond just deciding whether we reject or fail to reject the null hypothesis. So you've learned how to go through the 5 steps of hypothesis testing and come to a conclusion about whether you think you should reject or you have enough evidence to reject a null hypothesis, or in other words, claim support for your research hypothesis. And that is just the beginning of the way that we draw conclusions as researchers. So we know that every time we have a research conclusion, every time we draw a conclusion about whether to reject the null hypothesis or fail to reject the null hypothesis, that there's more to the story. We know that we could be making a decision error. We also know that effect size will matter, right? If it's just because something's statistically significant doesn't necessarily mean that it's meaningful. So that's what we'll talk about when we get to effect size. And then also our ability to reject a null hypothesis when we should be rejecting a null hypothesis is called statistical power. Okay, so those are the 3 things that we'll cover in this lecture. Let's start with decision errors. Decision errors occur when we go through the steps of hypothesis testing correctly. We do everything correctly, but we get the wrong conclusion. And I want to go back to an example that I introduced a couple weeks ago, where we were first getting into hypothesis testing. And I gave you an example where I said, it's kind of like deciding whether you're in the real world or the matrix world, right? It's all based in probability. If I can't know for certain at any given moment if I'm walking around in the real world or the matrix world, right? I can gather evidence from my experiences in the world that will help me decide what world I think I'm in, right? And I can gather evidence perfectly. I can do it really scientifically. I'm not making any mistakes. I'm not miscounting the number of blue jays that I'm experiencing in the world. I've counted them correctly. I've tracked my experiences correctly. And because I've seen a whole bunch of blue jays, I think I'm in the real world, right? I conclude I'm probably not in the matrix world because blue jays are really rare in the matrix world. I think that I have enough evidence that I'm in the real world. Okay. I could, of course, be wrong. I could always be wrong. I might have just seen some really rare blue jays, right? And still be in the matrix world. There is a small chance that that has happened. The same thing can happen when we get into hypothesis testing, right? I could see a test statistic that is so extreme that it falls out in my rejection region, right? Remember, when we're doing a z-test, we have a normal distribution for our comparison distribution. Okay, this represents a distribution of all the possible results that could occur under the null hypothesis. So there's some variation. Most samples would have a mean somewhere on the middle. And then there are some samples that would have means on the lower end or on the higher end, right? And say we're doing a one-tailed test. If my test statistic falls out in this rejection region, I reject my null hypothesis. I say, okay, that's pretty unlikely under the null hypothesis. That's an unlikely value on my comparison distribution. And I would decide appropriately to reject my null hypothesis. However, that's based in probability. It's not based in fact. So I could be making a mistake. And there are actually two different ways that I could be making a mistake, or two types of decision errors in hypothesis testing. The first one we call a type 1 error, and this is it's a capital I, it's actually Roman numeral 1. Okay, so type 1 error. And this is an error where we make a decision to reject the null hypothesis when in fact the null hypothesis is true. And I'll explain this in a little bit more detail in a second. But it's important to understand some things about type 1 errors. The probability of making a type 1 error is always going to be equal to the significance level. Okay? And that's the significance level that you chose for your test, also called alpha. So this is new terminology I'm introducing. You might have come across it in the textbook. Your alpha level, or alpha, is the significance level that you've chosen to use for your test. So for example, if you decide that you are going to evaluate your test statistic at the p is less than 0.05 level, okay, so you're going to use the cutoff values that correspond to a probability of 5% falling in your rejection region, 5% of the distribution in your rejection region, or p is less than 0.05 to evaluate your test statistic, then the probability of making a type 1 error in that test is going to be exactly 5%. Or if you decided to use the more conservative cutoff values or evaluate your test statistic at the p is less than 0.01 level, or use alpha of 0.01, in that case, you would have a 1% chance of making a type 1 error. Let's walk through an example to help make sense of this. Let's imagine that we're testing a new drug for cancer treatment. We're just going to call it XX, and this drug would be used in addition to chemotherapy. So all of our patients are undergoing chemotherapy. And we have a sample of 10 patients who are also going to receive drug XX in addition to their chemotherapy treatment. We perform a single sample Z-test, that's the test you've learned about, and based on the results, we do everything correctly and we decide to reject the null hypothesis. And recall, if you reject the null hypothesis, which would mean that the individuals who got drug XX have a mean symptom rate that is equal to the mean symptom rate for patients who only underwent chemotherapy alone. Okay, so mu1 is equal to mu2, that the mean symptom rate is the same for these two populations. That's the null hypothesis. So remember, if I reject my null hypothesis, then I'm saying I have evidence for the research hypothesis that the individuals who have this drug actually have a different symptom rate than the individuals who underwent chemotherapy. Or in other words, I think this drug might work. Okay, so let's imagine that we did that study, I reject the null, and I have evidence for the fact that this drug actually improves symptomology over and above just chemotherapy. Okay. However, in reality, in the real world with the capital R, real world, the truth with the capital T, drug XX does not actually have any benefit over and above chemotherapy. Okay, so I might have just seen in my sample that my patients seemed to have a symptomology rate that was pretty low. And I concluded, based on my statistical test, that it was low enough to support the research hypothesis, right? They had a mean symptomology rate that resulted in a Z statistic that was extreme enough to conclude that these two populations are different. However, that difference in the real world was a fluke, okay? Because in the real world, the drug doesn't work. What happened here? Well, we made a type 1 error. We falsely concluded that the extreme score, the extreme improvement rate, was due to our manipulation. It was due to the drug. However, I just got an extremely rare result by chance, right? So it happens, those people under just chemotherapy could possibly just do really well sometimes. I might have gotten a sample of individuals who just happened to be doing really well, right? Compared to people who are typically treated with chemotherapy, right? My sample was treated with chemotherapy and a drug that was having no effect, right? But they happen to be doing pretty well. They happen to be some of the people doing the best under chemotherapy treatment, which made it made it appear to me that my drug was working. That is a type 1 error. As I mentioned, there are two different types of errors in hypothesis testing. The second type of error is called a type 2 error, not surprisingly. So this is the Roman numeral 2, or double I. And this error occurs when we fail to reject the null hypothesis, or we conclude that we should not reject the null based on our 5 steps of hypothesis testing. But in fact, in the real world, the truth with a capital T says that we should have rejected the null hypothesis because the null is false, okay? And the probability of making a type 2 error is beta. We call that beta. So remember, the probability of making a type 1 error is equal to alpha. The probability of making a type 2 error is called beta. That's the Greek letter beta. So walking through a similar example, let's just say we're testing this new cancer drug again, and this time we're starting fresh, right? This time I do my single sample z-test, and based on my findings, I say, ooh, the drug isn't working. It doesn't look like it's providing any benefit above and beyond chemotherapy based on my statistical test. I was not able to reject the null hypothesis. So based on our test, we failed to reject the null, and therefore we cannot conclude that the drug has any benefit over and above chemotherapy. However, in this example, in the real world, it really works. The drug is working, and in my study, I failed to detect that it was working. This is called a type 2 error. And this happens because the real benefit of the drug, it exists, but it's a small benefit. So my z-score just wasn't large enough to be detected in my test as passing or surpassing statistical significance, right? Or surpassing my threshold for significance. This is called a type 2 error. And just to reiterate, these errors are not human errors. They happen when we do everything correctly, but we end up with a wrong conclusion. So we know every time we do a statistical test that there's some probability that we are making a type 1 or a type 2 error. So because we know that that is always going to be a possibility, or in fact, there's always a chance that we're making a type 1 error or type 2 error, we try to make the likelihood of those errors as small as possible. And we do have some control over that as researchers. And what we do know is that these two errors work in balance of one another. If we decrease the likelihood of making a type 1 error, then we are increasing the likelihood of making a type 2 error, and vice versa. So for example, if you think about it, I can move my significance level, my alpha level, to 0.01 to reduce my likelihood of making a type 1 error, right? Remember that if my alpha level is 0.01, then I have a 1% chance of making a type 1 error. Okay. But if you think about what you're actually doing when you make that decision, you're moving your threshold from the 0.05 significance level over to the 0.01 significance level. So there's 5% of scores in this whole region, but there's only 1% of scores in this region, right? So we're pushing the threshold for significance further into the tail, okay? And when we do that, we are decreasing the chance of making a type 1 error. That's good, right? Yes, but we're also making it harder to reject the null hypothesis, right? Because now I need an even more extreme test statistic or z-value for my sample in order to get it into my rejection region, because now my rejection region's out here instead of out here, right? So my rejection region's further away. It's going to be harder to reach that criteria, which means that it's going to be harder to reject my null hypothesis, increasing my chance of making a type 2 error. Okay. Alrighty, so this is a little grid that shows the kind of 4 different scenarios that could be happening underlying our statistical test. Right, so we go through our whole study and we draw a conclusion, okay? And that's this side here. So we draw a conclusion as researchers. I either decide to reject my null hypothesis or to fail to reject my null hypothesis, okay? So that's what happens as a result of my study. And then in the real world, which we don't know, we'll never know what the real world is, right? Remember, we never know if we're in the matrix world or the real world. Similarly, we never know if the null is actually true or false. So in the real world, the null is true or the research is true. Okay. So if the null hypothesis is actually true and I reject the null hypothesis, right? So I reject it. I say I have statistical significance, but in fact I'm wrong. And the null hypothesis is true. Remember, that's where I've made a type 1 error. So that's what we just talked about. We also talked about a type 2 error where I say, I can't reject my null. It doesn't look like I have significant findings, but in the real world, I'm missing it. I'm missing the effect because in the real world, there is something happening. The research hypothesis is true. We're up here, right? The research hypothesis is true, but I conclude that it's false. That is a type 2 error. So there's some probability alpha. There's an alpha probability or a probability equal to alpha that I'm making a type 1 error. And there's a probability equal to beta that I'm making a type 2 error. And then, of course, there is some probability that I'm not making any errors and I'm drawing the correct conclusions, the appropriate conclusions. And so those fall in the off diagonals here. I could be rejecting the null hypothesis when I should, in fact, reject it because it's false. Or I could be failing to reject my null hypothesis correctly because the null is true and I shouldn't be rejecting it. So those are the 4 possibilities. I'm going to move away from type 1 and type 2 errors and talk about effect size. Remember that if the 2 population means are exactly the same, that means there's no effect at all, right? The 2 populations are the same. But as those population means move apart and the distributions are becoming more distinct, then it seems like, oh, maybe these populations are different from one another. Maybe there is some sort of effect here. Maybe my treatment is working, right? So as those means are moving further and further apart, the effect size, we say, is increasing. Okay, so effect size is the magnitude or amount of difference between the two means. Okay. However, we do need to take into consideration the variability of those distributions. So we need to consider how those distributions within themselves are spread out. And then taking that into consideration, how are these two means spread out from each other? So I'll show you the formula and how we take that all into consideration to calculate effect size. Another way to think about effect size is that it's the extent to which the two populations do not overlap. So the extent to which they're distinct. So recall that hypothesis testing, the whole process and our conclusions that we draw from hypothesis testing are just all or nothing. We either reject the null or fail to reject the null. Or we say there's an effect that's statistically significant, or I can't conclude that there's an effect. Okay. But sometimes I want to know how much population 1 differs from population 2, right? Sometimes I want to know more than just, is there a statistically significant finding? Sometimes I want to know how big is the difference between these two groups, whether or not it's statistically significant. And of course, I could just look at the two means and figure out what the difference between those is, but that wouldn't take into consideration variability. So effect size is a little bit more sophisticated, and it will tell us how far apart the means are, how different the groups are, or different the populations are, more appropriately, taking into consideration the variability of those distributions. The statistic that we'll use for effect size is denoted by the lowercase letter d, and that is called Cohen's d. It's named after the statistician who came up with this measure. Okay. So Cohen's d is going to be defined by the distance or the difference between the two population means divided by sigma. And you know that sigma is the population standard deviation, right? It's a population parameter, and it's the standard deviation parameter. And specifically, it's the standard deviation of population 2. Remember, when you state your populations, this is the standard deviation of population 2, and we actually we make an assumption here that the two populations have the same spread or the same standard deviation. Okay. This assumption is called homogeneity of variance. Okay. And then given that we make that assumption, we want to just test how far apart the two population means are. So for example, if I want to calculate the effect size for my new cancer drug XX, we test the recovery rates in a sample of 10 individuals, so it's the same example, and the mean recovery rate for my 10 individuals who get drug XX is 70%. So the mean recovery rate for my sample is 70%. And I want to compare that to the rate from the population, which those people only get chemotherapy. Okay, so that's my comparison group. So population 2 is people who only go through chemotherapy treatment. And the mean recovery rate for that population, for population 2, is 50%. And we also know that the standard deviation is 10%. Okay, so 50%, give or take 10%. So 70 minus 50 divided by 10, and I get Cohen's d equals 2. Cohen laid out some conventions for interpreting your effect size coefficient, or your Cohen's d value. First, the threshold for a small effect size is 0.2. And this would mean that there's a lot of overlap between your two distributions, and that the space between those two distribution means is pretty small, okay, because they're pretty overlapping. In other words, if you think about what this means, it means that most of the people in population 1 have values that are the same, roughly the same as the people in population 2, right? A medium effect size would be 0.5. So this means that there's less overlap of the two distributions. They're spread further apart from one another, meaning the means are further apart from one another. And this means that the people in population 1 are a little bit more different than people in population 2. And finally, the threshold that Cohen laid out for a large effect size is 0.8. And 0.8 means that there's even less overlap of your two distributions. And in other words, the mean of those two distributions is further apart because the whole distribution shape, they're moving away from one another. Okay, so the mean over here is further apart from the mean over here. And this, in other words, means that there's less similarity on your underlying variable between your two populations, or between the individuals in these two populations. And this is important because it helps us understand our findings a little bit better. So let's consider I have a new drug and it claims to make you smarter, but it has to be injected. And it costs $200 a bottle. But I've done this study and it does have statistically significant results, right? Over an 8-week period, it's going to make you definitely smarter. In fact, it's going to increase your IQ by 0.5 IQ points, right? My effect size is 0.2. Would you buy this drug? I don't know about you, but I would not think about buying this drug, right? It might statistically significantly improve my IQ. However, only by 0.5 IQ points. And given the context, given that this is a drug that needs to be injected, it's new, I don't know what the side effects are, it's really expensive, that's not worth it to me. Going through that process for just a small effect size, I don't care whether it's statistically significant, I don't want this new treatment. But let's consider a new drug that claims to make you smarter, that costs $2, and it's a pill that you ingest only one time. And it's shown to have immediate statistically significant results. Lots of studies have confirmed. And there's an average effect size across these studies of 0.9, meaning that it will increase your IQ by 25 points. Might you be interested in buying this drug? I mean, some of you might be saying no anyway, because it's kind of creepy, but you can compare this to the previous slide, and this seems like a much better bet, right? So both studies are statistically significant. Both studies improve IQ based on the statistical test. Both treatments will improve your IQ, but the effect size for this example is a lot larger, and the context has changed. So for a large effect size and not a lot of risk, I might be willing to buy this drug. Importantly, effect size is related to statistical significance. So the larger the effect size, or the larger the difference between my two population means, the more likely I will detect a statistically significant finding in my study. And that should make kind of intuitive sense, right? If two populations are really different from one another, and I'm testing to see if they're different, then I should be able to detect a difference. However, that doesn't always work out that way. I can have a really large effect size and not be able to detect it in my study. And similarly, I could have a small effect size and my study still concludes that there's a statistically significant effect. And this is important to understand because it tells us that there's something more to statistical significance, right? So usually in our research manuscripts, we report statistical significance, but more and more people are expecting to also see a report of effect size. And with those two pieces of information together, we can get a better understanding of our research findings. All right, that's all I'll cover in this video, and I'll cover statistical power in the next video. Let me know if you have any questions.